here we're asked to classify each equation according to its type, whether it's linear, separable, exact, homogeneous, or Bernoulli, and then solve each equation using a different method. So let's look through these and decide which ones are linear and then which ones are separable and exact and so forth, and how can we identify them. Notice here these boundary values or initial values we don't need to really pay attention to here, but when we solve the equation we're going to want to use those to solve for our constants. But let's look at first linear. On this first equation I have my derivative term is fine. You want that to be by itself. Actually, the form for linear would be if you can write the equation in the form y prime plus some function of x, p of x, times y is equal to another function of x is equal to q of x. So notice that on this first one I could write this in linear form by bringing my y terms over to the left side and then factoring out the y. You've got y prime. When I bring those over, they'll both become negatives, and I'm going to factor out the y to give me an x plus 1, and then I'll be left with 2x plus 2 on the right side. This is linear. So this is linear. Let me, instead of writing that, let me just mark it off to the side that A is linear. I'll just put an L to stand for linear. Okay, on the second equation, it's not linear because we have this y to the third term. Remember that to be linear, all of our y terms have to be linear. On this third term, on these y's here, this should be e to the y power. Each one of these should be e to the y. And e to the y would make it not linear. Also, y squared is not linear. On this last term, because I have y in the denominator, that's also not linear. So the only equation that's linear is A. Okay, now let's look at separable. To be separable, you want to be able to write the equation, I'll do this here, in the form derivative equals some function of x times some function of y. So on this first one, I do have my derivative by itself. And on the right side, again, if you group these y terms together, you could factor out a y. So let me just group them together. Well, and let me factor out the y to give me an x plus 1. It's just like what I did over here. And then plus, notice that these two terms that we're left with have a common factor of 2, and so I could factor out a 2 to be left with an x plus 1. And then this x plus 1 factors to leave me with a y plus 2. So notice here I have my derivative written as a function of x times a function of y. This equation is separable. So for separable, I'm going to put an S here. On the second equation, if I isolate that y prime, I'm going to bring this y over to the right side, and then I'm going to divide by 2. We'll be able to write this as y prime equals y to the third plus y, that's bringing the y over, and then dividing by 2, we're given this equation. And I can consider this to be multiplied by 1, so I have a function of y, and 1 is considered to be a function of x, or a function of any variable. So B is also separable. Okay, and C, let's see. In order to get my derivative by itself, I'm going to have to bring this term over to the right side of the equation. That's going to give me x e to the y plus x y e to the y dy equals y e to the y dx, and then I want to divide both sides by dx and divide both sides by this numerator, and notice that that numerator has an x e to the y in common. I'm going to factor that out, and that'll leave me with a 1 plus y. So that's what I'm dividing by here. X e to the y times 1 plus y. That's going to give me my derivative on the left side, dy dx, and on the right side, these e to the y terms are going to cancel. I'm going to write this as 1 over x times y over 1 plus y, so that I get my function of x times my function of y. And so C is also separable. On D, if I move all my terms over to one side and solve for dy dx, see, I'm going to bring these two terms over, 1 plus y squared, and then I'm going to divide by this coefficient of dy dx, 2 x plus 1. Notice that I have my function of y, this 1 plus y squared, or 1 plus y squared over 2, however you want to think of it, is a function of y. And then 1 over x plus 1 is a function of x. So D is also separable. And then E already has the derivative by itself, and you have your function of x times 1 over y, the function of y. So all of these are separable. That's nice. Okay, now exact. To be exact, let me do exact up here. To be exact, you want a function dy plus, actually this was dx, I think, in the book, plus another function times dy is equal to 0, and to be exact, the partial derivative of m with respect to y has to equal the partial derivative of n with respect to x. So for exact, we want the equation equal to 0, and we want to write these equations in terms of differentials. So wherever we have y prime, we're going to write it as dy dx we want all the terms over on one side. So here I'm going to bring all these terms over. That's going to make them all negative. minus xy minus 2x minus y minus 2. If I put a plus here and put all those in parentheses and then multiply by dx, this is the form that I want that in order to test to see if this is exact. Here I'm going to have 1 dy plus this function dx is equal to 0. So my m is here, my n is 1, and I'm testing partial derivative of m with respect to y is negative x minus 1. Partial derivative of n with respect to x is 0, and those are not equal, and so A is not exact. On B, if I bring that y to the third over, I'm going to have, and then multiply by dx, I'm going to have 2 dy plus negative y minus y to the third dx equals 0. And again, to test to see if this is exact, I want to test the partial derivative. This is my m, negative y minus y to the third. With respect to y, notice I'm going to get negative 1 minus 3y to the second, and that's not going to be the same as my partial derivative of n with respect to x, which is 0. This is not exact. C is written like it may be exact. Here's my m, y e to the y, and my partial derivative of m with respect to y. I have to take the derivative of y. That's going to be 1 times e to the y plus the derivative of e to the y is e to the y. So I get y e to the y. And notice that is the same as the derivative, partial derivative of n with respect to x. When you take the derivative here with respect to x, these x's will drop out. You get e to the y from the first term, and you get y e to the y from the second term. So C is exact. D, if I multiply by dx, then I get 1 plus y squared dx plus 2 times x plus 1 dy equals 0. And if I do my partial derivative of m with respect to y, I'm going to get 2y, and partial derivative of n with respect to x is just 2. This one is not exact. And for the last one, if I multiply by y, I'm going to get y dy, bring the x over, and multiply by dx, I'm going to get minus x dx equals 0. Here's my m, partial derivative of m with respect to y is going to be 0, and the partial derivative of n with respect to x, because there's no x there, is also going to be 0. So E is also exact. Okay, now for homogeneous, what you're looking for is that all your terms have the same degree, and if you have any fractions, that those that the numerator and denominator have the same degree. So for homogeneous, if I look on the right side, Here I have a second degree term, and this first term, or the second term, is only a first degree term. This one is not homogeneous. On B, here my first term, y, is a first degree term, and y to the third is a third degree term. This one is not homogeneous. Here, with the exponent, in order to be homogeneous, if you have exponents, those exponents have to be raised to a fraction with the same degree in the numerator and denominator. If you have something like e to the y, it's not homogeneous. Now, you may be able to divide out the e to the y, like we did here. But even if you divide out the e to the y, you're still going to have a first degree, and second degree term. It still won't be homogeneous. On D, because you've got a 0 degree term and a second degree term and a first degree term, these are not homogeneous. And on this last one, here you have the fraction with a first degree at the top and first degree at the bottom. This one is homogeneous. So E is the only one that's homogeneous. And the last type is Bernoulli. An equation that's Bernoullian form looks almost linear. You've got the y prime plus p of x times, use my pencil, times y is equal to q of x. But then on the right side you've got this also multiplied by some power of y, times y to the n power. So when we wrote these equations as linear, if they're linear, they will not be Bernoulli. So A, we don't even have to check, it was linear. On B, notice that this is almost linear except for this y to the third. That you've got this derivative term, and even once you divide by the 2, you've got a first degree y term, that's the linear part, and then on the right side of the equation you're going to have this function of x. It's going to actually be 1 over 2 times y to the third. This one is Bernoulli. Let's see, on C, it's not Bernoulli because we have this function of, well, actually that e to the y cancels out, doesn't it? So let's see, once we cancel out the e to the y, we're left with this. And you may be able to take this y divided by y plus 1 and rewrite it. I'm gonna show you a trick. I'm gonna write this as y plus 1 minus 1 in the numerator. So I'm adding 1 and subtracting 1 so that I can break this up into y prime equals 1 over x times, if I take this y plus 1 over y plus 1, that's 1, minus 1 over 1 plus y. Well, I could rewrite that to make it a little bit simpler, maybe if you're going to do an integral. But I still have this y in the denominator, and I really can't get rid of it without multiplying this derivative term by y plus 1. So this one is not Bernoulli. This one, because I don't have a y term, is not Bernoulli. And on this last one, I have a y term here. I could maybe stretch this to say that it is Bernoulli, in that I could write this as y prime plus 0 times y equals x times y to the negative first. So there I have my y term. It's just that my function of x is 0. So if you write it this way, you could consider it to be Bernoulli. So there, Bernoulli. Okay, now the next part is actually solving these, and it says solve each using a different method. So let me get my highlighter out, and we know that this equation D has to be solved as a separable ODE. So that means this C has to be exact, B has to be Bernoulli, A has to be done as linear, and that leaves us with homogeneous for E. It tells us which method we're going to use to solve each ODE. So when you see something like this, and I will have something like this on the first test, you need to classify each one of the ODEs, give all the classifications that you can for it, and then solve each using a different method. Sometimes you'll be left where you can choose one method or the other. Here we don't have any choice. Since D was only separable, we had to do that one as separable, and then the other ones just fall into place.